Well, I want to welcome you all to this first ADAS Labs webinar, hybrid. And it's going to be the first one of a series of different webinars and seminars that we're going to be hosting here as part of the Automated Driving and Simulation Lab. So I'm Simeon Calva. I'm the director of the Automated Driving and Simulation Lab here in Delft, a lab which is intended to bring together a lot of the automated driving research in Delft, but also to reach out and connect with other universities and other researchers. And we're pleased to launch this series. And today we have Jonas as our first speaker. So I'm going to hand over to Said, who's helped organize this series, and he's going to introduce Jonas.
Okay, hello everyone. I'm glad to host the first series of the ADAS Lab seminars. We want to continue this series probably once per month or once per 2 months. Just to give a brief introduction to Jonas. Jonas is an associate professor in Chalmers University of Technology. He's focused on traffic safety and behavior analysis. I give you the floor to Jonas.
Thank you very much. Yes, so great to see you here and great to have the people online. I'm here to present to you the topic of validation of simulation-based crash generation on crash outcome severity. And this is a topic. I'm coming from the domain of safety, and I understand that many of you may come from the domain of more simulation infrastructure, traffic simulation, those kind of things. So I'm going to give quite a lot of general in the beginning, general introduction to the domain. And the why here, the question here is why this is needed, why I feel this is needed, and how it can be done. And let's see if this works. Okay.
Should put the mouse.
Yeah.
It should work now.
Yeah, and I really like to thank you for inviting me for this talk. Yes, who am I? I'm a professor or associate professor, depending on how you define it. In Sweden, we have something in between. So, industry research is where I started. I worked with traffic safety industry research for 10 years, both passive safety and in-crash and pre-crash safety. And then I've been in academia since 2008. And my research focus is on virtual safety assessments, but all the components: behavior modeling, crash causation modeling, the different types of assessments, methods, perspectives. And some of the current projects I'm involved in, one is V4Safety, which is a methodological EU project on how to do prospective safety assessments virtually. And there I'm leading the group and the work package on human in simulation. I'm also heavily involved in the Swedish project called GIDAS, where we focus on scenario generation and behavior modeling. Then I'm also involved in high drive, but to a less extent. And so the outline today is I'll start with the background, as I said, quite generally. What is traffic safety? How to improve traffic safety, and then how to assess traffic safety measures. Or measures here, I mean any measure that you take to improve safety. And after that introduction, I will talk about the challenges, some of the challenges in virtually assessing the safety of X, and I'll come back to what I mean by X here. Some challenges in baseline validation, the impact of behavior model choice in the assessment, how much that impacts the outcome, as well as an issue with mixing scenarios when using safety surrogates, when using near crashes or things like that when you to assess safety. The first two are directly related to a paper that's been quite recent, and then the last one is kind of a little bit of an extension to that. So, what is traffic safety? If we define traffic safety from the perspective of ISO, it's only about severe injuries and fatalities. So it's not about crashes; it's about severe injuries and fatalities. If we're talking about what the WHO and this global ministerial conference, it's also about mobility without risk of death or injury. So it's not about only crashes; it's about the risk of injury or death. And then, if you talk to the Swedish Road Administration, they say, crashes are fine. It's okay to have crashes. As long as you don't get injured, you can have as many crashes as you want from a traffic safety perspective. Then others consider this from a different perspective. You have insurance companies, of course, crash is a cost, so they want to reduce the number of crashes overall. But they also have the whole range, so they are interested in across the whole chain up to severe to fatalities or injuries. If you look at the individual, you and me, we are interested in costs. We're interested in trauma because it doesn't feel good to crash, but also how to get the kids to school and things like that if you crash, right? You have to repair the car. So there are different things. If you look at the car companies, they're basically mirroring the customer needs. But if you look at, for example, Volvo, they made this journey where they started out with focusing only on reduction of severe injuries and fatalities. Then they shifted to reducing the number of injuries. And now they're transitioning to trying to avoid all crashes, or which you shouldn't crash. But that said, they will likely be evaluated on the severe crashes and injuries when you're talking about the safety footprints, which is something that is being then pushed today, that companies should be able to show where they're at in terms of safety. So that's the background and the different perspectives you can have. How do you improve traffic safety then? Well, there are plenty of different ways of assessing safety. You have infrastructure, behavior, like mobile phone use and things like that. You have driver assistance systems, automated emergency braking, things like that, as well as autonomous driving. And how you improve things depends on the targets. Do you want to focus on the injuries, fatalities, or the property damage, crashes, or both? I would argue you should absolutely go for all of them, but the most important is still from a societal perspective is the injuries and fatalities. One main point here I want to make throughout this is that reduction of crashes doesn't necessarily need reduction of fatalities. And if we take a look at, for example, this is from the Vision Zero handbook, you can find it online. Studded tires, they explicitly write this. The studded tires cost more lives than they save. So what they do is that you can drive faster, but you crash. While if you're looking at the low speed conflicts, they will be reduced. So you're actually reducing the number of low speed conflicts, but you're increasing the number of fatalities, which is a problem. Then this is a bit debated then if you look at infrastructure, and if you're thinking about this only from a car perspective, if you're involving cyclists and more road users, it's a problem. But there are indications that there may be an increase in the number of conflicts, in the number of conflicts when you're introducing roundabouts, but where you have a reduction in the number of fatalities, a substantial reduction in the number of that. So that means that if you would judge a system, judge this purely based on number of crashes, you should never go with the roundabouts. But if you're looking at it from a fatality perspective, you should do that. Then it's not inconceivable that there is some in-vehicle technology that may actually reduce low severity crashes, but increase the severe ones, right? So the whole premise of this is that we need to look at the whole chain. We need to look at crashes because they're important, but we also need to look at the severe end of things. And that's where the validation of this comes in. So how do we then assess safety and a safety measure? Well, you have traffic safety impact assessments. It's a systematic evaluation process conducted to estimate the impact of the X here, the infrastructure, policymaking, in-vehicle systems, and so forth, on traffic safety, however you define that. And here I want to push for my view. This is my view of the two differences between safety assurance, which is to make sure that the system is safe enough to be sold for public use on the roads. And here, you don't not all of those components when you're doing this need to be representative. You don't need to, when you want to be able to show that your edge cases are solved, you want to show different things in terms of where you're not doing, saying that you're reducing something with certain percentages. But if you're looking at safety impact evaluation as per my definition, that requires representativeness. So you want to quantify the impact of a particular system, such as infrastructure or in-vehicle system, then it's about representativeness. You need to be able to show that it's representative in the world. This is then typically a reduction of number of crashes, injuries, fatalities, or something. And this can, of course, also be used then in the safety assurance, but then it could be, for example, the positive risk balance to be able to show what is the in relation to some benchmark, where do you stand? And all of this can be used for safety argumentation when you're arguing for example, releasing an automated driving vehicle on the road. The actual safety impact assessment, if you're talking about virtually now, we have baseline treatments. I need to define those. And we then want to compare this. I'll come back to this slide in a bit. What is baseline? It's a set of data which does not include a safety measure, and which is then serving as the benchmark. This can be defined in many different ways. Treatments is the data where you have the safety measure and you want to compare that. So that's just the basics. So you have this, you compare the simulation outcome, but you need to compare it on something. So the why here, what to compare on. Do we compare on crashes, TTCs lower than a certain number, or fatalities? So fatalities at the top, injury risk, different levels of injury, crashes, near crashes, cases time to collision less than something, which is basically a near crash, depending on how you define it. So then the bottom part of this is more the safety surrogates, where you have something you say, oh, I'm interpreting this as having an effect on safety at the end. And then you have to define what safety is. The assessments, you have baseline versus treatments, where on the bottom here you have some exposure. It could be kilometers driven, for example. At the top, you have whichever units that you want to metric you want to assess. When you're doing this can go really wrong. And the example I'm giving now, it's hypothetical, but things like this are being done. Maybe not by researchers, but it's being done. So let's say that we have an automated driving system, which is a treatment. We identified that there are 40 property damage only, 40 crashes with at least property damage only. They're driving 10 million kilometers, so we get 4 crashes per million kilometer, right? Then we have baseline, manual driving, and there we have 4 serious injuries. And we have 100 million kilometers driven. This means that we have 0.04 serious injuries per million kilometers. But that's 100 times worse. The treatment is 100 times worse than the baseline, right? Well, apples and oranges or bananas and pears or whatever you want to say. But it is really, you have to really keep track of what you're comparing. And that's another main message of this. It is so easy to think that you're comparing something with something else, and they're not the same thing. This was an example of a retrospective safety assessment that only uses historic data. So here's the timeline. We have a number of cases, and then we have a number of treatment cases, and you're comparing those. So that's history. We use them as they are. Now we're switching to virtual safety assessments. This is a prospective safety assessment, which means we're looking into the future. We're trying to predict what would happen if something else, if you have this treatment. A starting point here is counterfactual baseline simulation, which is what we typically do. And counterfactual here means we have a set of original crashes. We have the kinematics of those crashes. And so we have the pre-crash kinematics of those crashes. And we make some modifications to those. Typically, we remove some behavior and replace that by a driver model. So we have the original and we replace it by a behavior model. That means that we create variants of that specific case. So some of these original crashes will have a higher risk intrinsically. So they will generate more crashes when you're applying the model that you're applying. And some of them may not even produce any more if it just was by chance that this person looked away for 6 seconds or something like that in that particular case. So you will get a variety of different cases, crashes that you generate from this. And then you apply your system and you see out of all of these crashes that you generate, which crashed and which did not. Okay, which crashed and which did not. And then you compare those and do your assessments. And here you then don't think about exposure because exposure is already in there. And so that's intrinsic to the method. If we compare this to the completely behavior model-based baseline configuration, such as traffic simulations, there you generate some sort of future crash population where you create your baseline, And then you have a separate simulation, often most of the time, where you run your treatments. You could also apply them to whichever situation you generate the baseline if you want, but at least you're doing this. So here, the difference here is that first you can, they're running as different simulations. You can compare different lengths. You can run one at one length and just divide by how long that was and compare to the treatments. So these are just different ways of looking at it. And I think they're very complementary in the way that they're needed for safety. So they are called traffic simulations or stochastic scenario generation, depending on how, I'm pretty sure that's how I see it. So now switching to the issues. Validation is not easy. It's really not easy. I'll give a couple of insights that we got from this paper, but there are plenty more in the paper and also elsewhere. I'll be happy to talk with anyone about that if you're interested. Then I'm also going to show that the choice of behavior models really impacts the outcome. And then finally, this aspect of issue of mixing scenarios when using safety surrogates, or when you're using the lower severities to assess the higher severities. This is the paper that when I was contacted to talk about this, this was the paper that was referred to, and most of my talk will be around that. So we identified methodological challenges, but also we developed a crash causation model to generate crashes. And then the aim of the paper was to validate a real-end crash causation model for scenario generation, counterfactual. So original crashes, modify, and then apply to them. We wanted to address challenges in the validation process. We did that from different perspectives. I'll show one or two here. So the rest are on the paper. So the crash causation models, we have two of them. One is what we propose, which is a crash causation model that is a bit complex, but in detail, not. The most complex one is when you're talking about glance behavior. The other are relatively straightforward. Sleeping drivers or drowsy drivers, one component. Distracted drivers is another one, looking away from the road, how you're looking away from the road. Limited braking, drivers don't brake enough. They brake a bit until they think they're braking enough, but they could be braking much harder. Then too close, driving too close to the lead vehicle. So these are different components based on crash causation research. If we then instead take a more traditional model, which is you're taking the brake light and you're applying your reaction time after the brake light on the lead vehicle, and then you want to see, then there's going to be a reaction after that. So those are the two models we're comparing. What we're starting with then when we're doing the simulations, these here are, you can't really see it and you're not supposed to, but they are kinematics, pre-crash kinematics, speeds. So we have a rear end situation here. So we have speeds of one vehicle and there's speed of another vehicle, and those two will interact in some way. What we do then is we remove the evasive maneuver of the following vehicle and replace that by a driver model. We keep the original, the one that's in the fronts. And then we replace it by driver models, two of them. Crash causation model, in the case of our proposed model, it's these four components, but then also a response model. So those are different. The crash causation generation model and the response model. And the response model responds to whatever unfolds in the situation. And we're now talking about short events, 5 seconds or something like that. It's not hours and hours of driving, it's 5 seconds per event. Simulation, you run your two simulations, and out comes some crash kinematics, which are very similar then to the original, and they should fit in that population. They should just be more of them. Okay, one important point here is that all of these crashes will be across all levels of severity. Because the way that these are generated, it will cause crashes that are very, very just bumping into the lead vehicle, up until really the full sleeping drivers driving straight into the lead vehicle. So you get the full range, and that's important when we come to the validation. This is what this type of simulation does. Similar to what I think in most cases traffic simulations would do. You generate situations that are from the very low end all the way up to however long you want to run your simulation, basically. So the validation here is to evaluate whether the generated crashes represent the real world crashes in whatever way they're designed. So then you need to think about metrics to compare. So you want to compare with the real world, between your simulation and the real world, what to compare, which data to compare against, and then how to do the comparison. The how to I won't cover much here. We do that a bit in the paper, but focus on metrics and which data here. And just to reiterate, representativity and representativeness. Safety impact says that for it to be valid, there needs to be, the generated crash needs to be representative of whatever you want to assess. So if you want to assess crashes, then they could be representative crashes. If you want to assess fatalities, they need to be representative fatalities and anything in between. So validation metrics. Here in this study, we work with delta V, which is the change in speed during the crash. So how the vehicle changes speed as it crashes. You want to compare the distributions of delta V with the simulated crashes versus the real world. And then we also looked at injury risk. I won't go to details here. Here you have some risks, some injury risk curves that basically are just transforms from the delta V, depending on what level of risk you want to look at. So MI6 is the highest risk, and then while 1 is the lowest risk. Injury risk. So that's 1 could be a broken thumb or something like that, or broken bone, while 6 could be fatalities. We're not validating on crash frequency because this method is inherently not considering exposure. It's inherent. So if you look at the differences for traffic simulations, for example, it's stochastic, where that is by far the most common. And we try to find literature, and we can only find one that actually assesses on delta V from that type of simulations. If you have any other studies that you know of, please contact me because we're interested. Yes. So what data to compare on? GIDAS, many of you may know about that. It's a German data set. It's probably one of the world's best when it comes to the data that's been captured. It's only crashes involving personal injury, and it's collected around Dresden and Hanover in Germany. And there is a subset of these that are reconstructed to the pre-crash kinematics. So you have the time series of data prior to the crash. What you see here is a subset of these rear-end crashes, where we simulated the rear-end crashes again in our simulation environment, and we got delta V's. So the x-axis here is the change in speed. What you can see here is clearly that it doesn't have much to the on this side, on the low end side, right? Because it only includes crashes with personal injury. So of course it can't have much there. And that's even though 70% of all crashes or so, and depending on how you define a crash here, is property damage only crashes. So that's the graph, that this distribution is excluding 70% of all crashes to start with. Then also it has a substantial selection bias. Here, what this figure shows is that in that region, there's approximately 70% probability that a fatality is captured in the data collection. 60% chance that severely injured are captured, but only about 30% that a slight injury is captured. So that means that the whole data is going to be skewed towards the fatality, the fatal. So this can be adjusted for. You can just reweight it, and that's what we've done. So this is then weighted data. Now we have the same distribution as we had before, but now, and it's slightly reweighted. What we want to do now is to add the property damage crashes. And in the paper, we propose a method how to do that, where we're using data from an insurance company and some assumptions and so. So this is what it would look like. These are then 70% of the crashes, the lila ones. So this is approximately what we think it should look like if you capture the whole population of crashes in Germany that this GIDAS data is supposed to represent. But if we want to compare, so that means that we can't compare the original, with just the simulated crashes, because the simulated crashes are all. We could compare it directly to this, but we wanted to make it a little bit more generic. So what we did, we created a transform that basically implements the selection criteria, but just by fitting this sigmoid so that we get the best possible outcome. So if we apply this transfer function to the combined, we get what you have on this side, which is very similar to the GIDAS data. So this means that if we apply this transform, we're basically saying this transform captures the selection mechanisms that GIDAS has. So now by having that, we can use this and apply this to our simulated crashes and compare with GIDAS. So if we run our simulation, we can then we can apply the transform, and then we can compare to the GIDAS original data. This, of course, needs to be validated also for other scenarios and things like that, and they may be different for different scenarios, but at least it's a starting point, because otherwise you can't really do it. So, summary, we're validating the full severity range simulations, so crashes, with a transform. So we're transforming the simulated crashes into something that then can be compared to GIDAS data. So we propose this. So that's one part. I'm now going to talk about the choice of behavior models. Now we're using this. So we're using this transform on the simulations that we have. So we have a number of crashes from GIDAS, and we're using these two different models: the crash causation model, base model with the 4 components, and the brake light with the reaction time. And then this is the results from the first. So if we take our model and we generate crashes, it's going to be lots of crashes at the low end. But then we apply the transform, and we get this. And as you can see, the outcome is very similar, both in terms of the shape and the mean. It's quite similar for our crash causation model, which is an indication that this crash causation model is quite good. If we then apply the same we apply the brake light model in the same way, on exactly the same cases, we get this. So we get a substantial overestimate of the injury risk of the delta V, the mean delta V. And you see there's quite a long tail, much longer tail there, and thicker tail in the generated crashes with the brake light onset model compared to the one, our model, or compared to GIDAS. So this is one way to compare models and one way to validate models. It should be noted then, especially for any of these, we didn't tune the model to see, oh, we got these kind of results, but we actually we looked at literature. We wanted to see, we have crash causation models. We implemented those crash causation models and got this pretty good results on the crash causation side. And I know that for traffic simulations, for example, this may be too complex, but if you could boil this down to something that is simpler, then this type of validation method will also be relevant for that. Summary: a choice of behavior models has a large impact on the generated baseline, but also benefit assessment. I don't have time to go through that, but we have a previous paper where we looked at how much it impacts the actual. So depending on which model type you choose or model parameterization, how much the assessment also is impacted, and it's quite a lot, or it is a lot. So it's important to validate the full simulation chain. And just because you can't validate the outcome in terms of assessment, start with baseline. So you could develop your model for something that you know, and then you tune it, and then you run your validation there. And then after that, you can tune your parameters to fit whatever you want with those assumptions. But then at least you have done your validation on something that is available. And you can go from there and extrapolate some future scenario. We also did a sensitivity analysis. I don't include that here because it takes too much time, but it's the method of transform is relatively insensitive to parameter fitting, to exactly some of the assumptions that we made. So it seems to be quite robust. So that said, I want to shift to this other topic, which is a little bit outside of the topic of the paper, but it's related, and I'll come back to. So the issue of mixing scenarios when you're using crash surrogates or lower severity. Why this topic? Well, we've only demonstrated that the validation and model importance for one scenario. There are plenty of scenarios out there. Should we do everything scenario-based? Maybe, maybe not, but we need to know what we're doing when we're looking at multiple scenarios. Here, it's not obvious how to sum the scenario contributions to safety, the safety impacts. And that's what I'm going to show now. So issue, the relationship between safety surrogates, lower and higher severity crashes is not the same across scenarios. So you could have many near crashes for one scenario and very few fatalities, or very few near crashes and very many fatalities in relation. And that really matters if you want to sum them. So I'll give you an example of that. So summing these impacts is problematic. I guess many of you will know about Heinrich triangle, which is this assumption about fatalities being very few at the top, and then going down all the way down to some benign, or here it's called unsafe acts. So that's a pyramid with more and more going up. So this is the traditional way of looking. This is quite old, and it's the foundation for many of the conflict theories and things like that. So why we can use safety surrogates. But what does it look like in reality? This is hypothetical data. I'll show you some real data in a bit, but let's start with the hypothetical here. So let's say we have a scenario X, and that has 100,000 unsafe acts and 10 fatalities. In the other case, we have scenario Y, which could be straight crossing path, the other one rear end, where we have quite 20,000 unsafe acts, but 100 fatalities. So you see there is quite a difference there. So if we now zoom in only on the unsafe acts and the fatalities, so that means we have 100,000 unsafe acts, 20,000, 100 plus 20,000, and then 10 plus 100. If we now simulate the lower part, we take the unsafe acts, we take those, and we generate something. We apply our system to that. That means that we get some kind of performance. And let's say that this performance is now 80% reduction in the number of unsafe acts for scenario X, and 20% reduction in the other one, the Y. So we have different performance of this system for different scenarios, and that's absolutely possible, right? If you have a system that primarily addresses rear end, you will have mostly addressing rear end, while in sections is not going to be addressed in the same way. So this is what it could look like. That means that in total we have 70% reduction in these unsafe acts. If we now assume proportional reduction of fatalities to fatalities, so we take the same proportions for each scenario and just think of in the real world, if there then in the real world would be the same proportion as we identify here, then we would have 8 fatalities and 8 fatalities of scenario X and 20 for scenario Y. Right? Then we're just transferring that to the fatalities. That means we have 28 and 25% reduction. They're not the same. So you're assessing your system of unsafe acts, saying we got 70% reduction. while in reality, you got 25% when you're looking at the fatalities, because you're mixing the scenarios. There's actually been several publications, 2012, I think 2 or 3 publications that are showing this problem, but I wanted to highlight it because I really think it is a problem when you're mixing scenarios and looking at the surrogates or near crashes for that matter. So this is then assuming a proportional reduction of fatalities. As I talked about right in the beginning, there is also a possibility that there is the opposite effect. You have systems where a reduction of near crashes or lower severity crashes actually is just that, while you have an increase in the number of fatalities, like the studded tires. So that is on top of this. So you have those 2 different perspectives to consider when you're merging data on surrogate measures or lower severities to assess higher severities. Now I'll give you an example of real-world data. This is from the Sharp Tube naturalistic driving study. This is data that was collected over 2 years for over 3,000 cars. And they have different levels of severity. You have near crashes, minor crashes, police-reported crashes, and severe crashes. This study cost like $100 million or something like that in total, the whole study. On the right, you have different scenarios. So here you have rear-end striking, you have sideswipe, you have crossings and things like that. And what you have, these nice colors that you see, is just the proportions between the different scenarios, how they contribute. So if we zoom in and we take a look at this perspective, so we look at the pyramid and we look at the actual proportion of rear-end striking. So that means we have quite a few near crashes, we have very few minor, and then it's a bit increasing. So this is what it looks like in the Sharp 2 data. I should say that this is different, and this is a little bit of a different problem from what I looked at before, because this also includes selection bias. Near crashes, for example, are selected in a certain way in Sharp 2, but it gives you an idea of the problem. Turning to path has very few near crashes, a lot of minor, and then going up. So this is illustrating a similar concept to what I showed before when we looked at the differences between different scenarios. So again, if we want to do an assessment here, we can't just merge things, the reduction of number of near crashes, because that's not going to give us, it's going to give us information about near crashes. It's not going to give us information about fatalities. Okay. So the consequences of this is that assessing safety impacts, summing contributions may result in erroneous estimations of the impacts. So this really care has to be taken there. Yes. So then, to finish off, the overall summary of this is that it's important to know and adjusting for differences in simulation and validation data. Just don't assume that they're the same. And you have to think about how to make them comparable, apples and apples, and nothing else. The choice of drive-by-wave model impacts both baseline and assessments. I haven't shown about the assessment here, but the baseline I clearly showed how that works. And I also showed that the proposed model is quite good. And then finally, assessment of crashes is not the same as assessment of fatalities. And a safety measure may cause more crashes while reducing fatalities. That was in the beginning, the roundabouts and the studded tires and the potential automated vehicles there. And mixing scenarios when using safety surrogates is problematic. Okay. Thank you. Questions?